Welcome to Chapter 11, Part 3, Performance Evaluation. In this section, we will explore how to evaluate the performance of data mining models. Let's get started. Data partitioning is the process of dividing a dataset into training, validation, and sometimes test datasets. A common practice is two-way random partitioning to generate a training set and a validation set. The training data trains the data mining algorithm, while the validation set provides an unbiased assessment of the predictive performance of the models. Performance evaluation is the process of comparing the values predicted by the model against the actual values of the target variable. By assessing performance evaluation metrics, the analyst can then fine-tune the model to improve the performance of the model. In supervised data mining, sometimes three-way random partitioning is used to generate training, validation, and test datasets. The test dataset evaluates how well the final model would perform on a new dataset that it has never seen before. This method is implemented with the holdout method rather than k-fold cross-validation. Some supervised data mining algorithms may involve very rare target class cases. Oversampling involves intentionally selecting more samples from one class than from other classes to adjust the class distribution. This leads to predictive models that are more useful in predicting all target classes. Only the training set is oversampled, while the validation and test sets maintain the original class distribution. A model that fits a set of in-sampled data well may not predict new observations accurately due to overfitting. Overfitting occurs when a predictive model is made overly complex to fit the quirks of a given sample, accounting for noise rather than patterns. This compromises the predictive power for new samples. Data partitioning and cross-validation can be used to detect overfitting and provide an objective assessment. Performance measures for classification models can be computed from a confusion matrix, which summarizes classification outcomes from the validation data set. Common performance measures include misclassification rate, accuracy rate, sensitivity, precision, and specificity. These measures help assess model performance and fine-tune the model. The misclassification rate is the overall proportion of observations that are misclassified, while the accuracy rate is the overall proportion of observations that are classified correctly. The accuracy rate is calculated as 1 minus the misclassification rate. Sensitivity, also called recall, is the proportion of target class cases that are classified correctly. Precision, also called positive predictive value, is the proportion of the predicted target class cases that actually belong to the target class. Specificity is the proportion of non-target class cases that are classified correctly. Recall the Fashion Tech example from the introductory case where Class 1, target, is the group of social media users who purchase at least one product after receiving a promotional message, and Class 0, non-target, is the group of social media users who do not make a purchase after receiving a promotional message. We can calculate and interpret the accuracy rate, sensitivity, and specificity for this example. The number of target class cases that are classified correctly referred to as true positives in the formula, also known as sensitivity or recall, is 30, the false positives in 19. The proportion of non-target class cases that are classified correctly referred to as true negatives, also known as specificity, is 133 and false negatives are 19. The proportion of accurately classified records is 30 plus 133 divided by 30 plus 133 plus 18 plus 19, resulting in an accuracy rate of 81.5%. The number of target class cases that are classified correctly referred to as true positives in the formula, also known as sensitivity or recall, is 30, the false positives in 19. The proportion of non-target class cases that are classified correctly referred to as true negatives, also known as specificity, is 133 and false negatives are 19. The proportion of accurately classified records is 30 plus 133 divided by 30 plus 133 plus 18 plus 19, resulting in an accuracy rate of 81.5%. Before we move on in our examination of performance evaluation, it is important to note that the cutoff value set for classification models can influence the confusion matrix. For this course, we will keep to a cutoff value of 0.5, A cumulative lift chart shows the improvement that a predictive model provides over a random selection in capturing the target class cases. It allows us to determine the point at which the model's predictions become less useful. A high lift number is desirable, indicating that we can capture a large proportion of the target class cases by focusing on a small portion of cases with a high predicted probability. The number of cases is on the x-axis, and the y-axis is the cumulative number of target class cases identified by the model. The orange line is the baseline model, and the blue curve is the lift curve, which shows the ability of the classification model to identify Class 1 cases. Cumulative lift charts show how well a model performs compared to random selection. The higher the lift number is, the better the predictive ability of the model. The decile-wise lift chart also shows a graphical comparison of the predictive model performance in comparison to a random selection. This chart shows that the lift for the first 10% of the observations is about 7.1, which means that the top 10% of the observations selected by the model contain 7.1 times as many Class 1 cases as the top 10% of the observations that are randomly selected. The second decile, the lift values drop below 1, suggesting that the model will capture fewer target class cases than random selection in the subsequent deciles. Therefore, in this case, we would focus on the first 20% of observations that have the highest predicted probabilities of belonging to the target class.
The ROC curve shows the sensitivity and specificity measures across all cutoff values. A good predictive model will have a ROC curve that lies above random guessing. The greater the area between the ROC curve and the baseline, the better the model is.
The overall performance of the model can also be assessed using the area under the curve AUC measure. The predictive performance of supervised data mining models is based on the prediction error using the validation or test data. Common performance measures include root mean square error, RMSE, mean error, ME, mean absolute deviation, MAD, mean percentage error, MPE, and mean absolute percentage error, MAPE. These measures help assess the accuracy and bias of the models. The two most commonly used performance measures that capture the magnitude of the errors are RMSE and MAD. They both range from 0 to infinity, with lower values indicating a better prediction model. RMSE will always be equal to or larger than MAD. Thank you for your attention. This concludes our discussion on performance evaluation.